Hello students, today I am going to give lecture on some parts of Unit 2 of Elementary Communication Engineering. Please go through the contents. Now I will give you some basic idea of modulation. You can see in this diagram that in the modulation process, two signals are used. One is carrier signal and another is modulating signal. The modulating signal is nothing but the information signal. And now the question is, what is carrier signal? So carrier wave is a waveform that is modulated with an information bearing signal. Note that information bearing signal for the purpose of conveying information, So the modulating signal is nothing but the information signal, while carrier is a high frequency sinusoidal signal. For modulation, the device name is modulator, and a demodulator is a device that performs demodulation. Now, the next part is needs of modulation or its advantages. Sometimes baseband transmission has many limitations which can be overcome using modulation. Its quality is good and increase the range of communication, and also it avoids mixing of signals. So, reduction in height of antenna, quality is good, avoid mixing of signals, these all are needs of modulation or its advantages. And also the basic needs of modulation is to increase the bandwidth of the signal and to multiplex more number of signals. So modulation is need basically to multiplex more number of signals. Now we will go through the types of modulations. There are two types, continuous wave modulation and another one is pulse modulation. In continuous wave modulation, there are amplitude modulation and angle modulation. And angle modulation also divided into two forms. One frequency modulation and another one is phase modulation. And in pulse modulation, there are two types, analog modulation and digital modulation. In analog modulations, there are PAM, PWM and PPM. Pulse amplitude modulation, pulse width modulation and pulse position modulation. And in digital modulation, there are PCM, pulse code modulation and delta modulation. So, there are basically two parts, one analog modulation system and another one is digital modulation system. Now, I am going to explain you some important definitions. First, modulation index. It is very important in frequency modulation because it decides the bandwidth of FM wave and also it decides the number of sidebands. It is the ratio of frequency deviation to modulating frequency. If I assume the modulating index is MF, so MF equals to del F divided by FM. Del F means frequency deviation and FM means modulating frequency. In AM, the value of modulating index is 1. In FM, the value of modulating index is greater than 1. Now, deviation ratio. In a frequency modulation system, the ratio of the maximum frequency deviation of the carrier to the maximum modulating frequency of the system. And the next part is percentage modulation. In a frequency modulation system, the ratio of the actual frequency deviation to the maximum allowed deviation. I believe that this is clear to all. Moving to the next part, performance comparison between FM and AM. In FM, amplitude of FM wave is constant, and in AM, amplitude of AM wave will change with the modulating voltage. Next, all the transmitted power is useful, and in AM, carrier power and sideband power are useless. FM receivers are immune to noise, but in AM receivers are not immune to noise. In FM, bandwidth depends upon modulating index, but in AM, bandwidth doesn't depend upon modulation index. Bandwidth, the value of bandwidth in FM is 2 into del F plus FM, and here bandwidth equals to 2 FM. Next, bandwidth is large in FM, and in AM bandwidth is less than FM. There is a diagram, both FM and AM. So now, there is a question that which is better, AM or FM? From the comparison, we can see that FM is better than AM because FM is less prone to interference than AM. FM has better sound quality due to higher bandwidth. Actually, we know in FM, the carrier wave is modulated in amplitude by the signal that is to be transmitted, and in FM is the encoding of information in a carrier wave by varying the frequency of the wave. So, FM is the encoding of information in a carrier wave by varying the frequency of the wave. Now, we will go through the performance comparison between FM and PM. So, frequency modulation and phase modulation. In frequency, deviation is proportional to modulating voltage, and in PM, phase deviation is proportional to the modulating voltage. In FM, it is possible to receive FM on a PM receiver, and in PM, it is possible to receive PM on a FM receiver. In FM, noise immunity is better than AM and PM, and in PM, noise immunity is better than AM but worse than FM. FM is widely used. PM is used in some mobile system. In FM, the frequency deviation is proportional to the modulating voltage only, but in PM, the frequency is proportional to both the modulating voltage and frequency. Now, the most important part is sampling theorem. Sampling of the signals is the fundamental operation in signal processing. A continuous time signal is first converted to discrete time signal by sampling process. The sufficient number of samples of the signal must be taken so that the original signal is represented in its samples completely. Also, it should be possible to recover or reconstruct the original signal completely from its samples. Now, the statement of sampling theorem. Number 1. A band limited signal of finite energy which has no frequency component higher than FM Hertz is completely described by its sample values at uniform intervals less than or equal to 1 by 2 FM second apart. And number 2, a band limited signal of finite energy which has no frequency component higher than FM Hertz may be completely recovered from the knowledge of its samples taken at the rate of 2 FM samples per second. So, the first part represents the representation of the signal in its samples and minimum sampling rate required to represent a continuous time signal into its samples. And the second part of the theorem represents reconstruction of the original signal from its samples. Please go through the diagram of the sampling theorem which I explained to you on the previous slide. Now, the next part is Nyquist rate and Nyquist interval. When the sampling rate becomes exactly equal to 2 FM samples per second, then it is called Nyquist rate. It is also called minimum sampling rate. So, when Fs greater than 2 FM, the signals are not overlapping each other. Hence, there is no problem in recovering the original spectrum. But when Fs equals to 2 FM, the signals are not overlapping, but they are touching each other. But when Fs less than 2 FM, the signals are overlapping and also touching each other. Actually, the signals are overlapping with each other. And then maximum sampling interval is called Nyquist interval. In this diagram, you see that the signals are overlapping with each other. In this diagram, a continuous band limited signal is sampled at a rate lower than Nyquist rate, that is Fs less than 2 FM. Then the signals overlap with each other. Hence, the signal is undersampled in this case, and some amount of aliasing is produced in this undersampling process. In fact, it is the phenomenon in which a high frequency component of the signal takes identity of a lower frequency component of the sampled signal. So, due to aliasing, it is not possible to recover original signal from sampled signal. Hence, the signal is distorted. So, to prevent the overlapping, low pass filter is used because it prevents all the frequency which are above FM Hertz. So the LPF is called pre-alias filter because it is used to prevent aliasing effect. I believe that this is clear to all. Basically, there are three types of sampling techniques as under number 1, natural sampling, number 2, flat top sampling, and number 3, instantaneous sampling. Out of these three, instantaneous sampling is called ideal sampling, whereas natural sampling and flat top sampling are called practical sampling methods. Now let us discuss of sampling techniques in detail. So natural sampling is a practical method and will be discussed here. In natural sampling, the pulse has a finite width equal to tau. Let us consider an analog continuous time signal xt to be sampled at the rate of fs Hz. Here it is assumed that fs is higher than Nyquist rate, so fs greater than 2 fm, such that sampling theorem is satisfied. Again, let us consider a sampling function Ct, which is a train of periodic pulse of width tau and frequency equal to fs Hz. The diagram shows a functional diagram of a natural sampler. With the help of this natural sampler, a sampled signal Gt is obtained by multiplication of sampling function Ct and input signal xt. So Gt equals to Ct into xt. When Ct goes high, the switch S is closed. And here A is amplitude of Ct. So the value of Gt equals to xt when Ct equals to A, and Gt equals to 0 when Ct equals to 0. So here Ct is the periodic train of pulse of width tau and frequency fs and frequency fs. Now flat top sampling. Flat top sampling, like natural sampling, is also a practically possible sampling method, but natural sampling is little complex, whereas it is quite easy to get flat top samples. In flat top sampling or rectangular pulse sampling, the top of the samples remains constant and is equal to the instantaneous value of the baseband signal xt at the start of sampling. The duration or width of each sample is tau, and sampling rate is equal to fs is equal to 1 by ts. So the figure shows the functional diagram of a sample and hold circuit, which is used to generate the flat top samples. Also it shows the general waveform of flat top samples in this figure. And it may be noted that only starting edge of the pulse represents the instantaneous value of the baseband signal xt. Also, the flat top pulse of GT is mathematically equivalent to the convolution of instantaneous sample and a pulse HT. So here the value of GT, or therefore GT, will be expressed as ST into HT. ST into HT. The frequency modulation is a type of angle modulation in which the instantaneous frequency, suppose Ft, is varied in linear proportion with the instantaneous magnitude of the message signal. So, a method of transmitting information using a radio frequency carrier wave. Frequency modulation is widely used for FM radio broadcasting and also used in telemetry, radar, etc. The FM modulator circuits used for generating FM signals may be put into two categories. Number 1, the direct method, and number 2, the indirect method. Here, varactor diode modulator is a direct method. The varactor diode FM modulator has been shown in here. A varactor diode is a semiconductor diode whose junction capacitance varies linearly with the applied bias. The varactor diode must be reverse biased. The varactor diode is reverse biased by the negative DC source, here minus VB. The modulating AF voltage appears in series with the negative supply voltage. Hence, the voltage applied across the varactor diode varies in proportion with the modulating voltage. This will vary the junction capacitance of the varactor diode. The varactor diode appears in parallel with the oscillator tuned circuit. Hence, the oscillator frequency will change with change in varactor diode capacitance and FM wave is produced. The RFC will connect the DC and modulating signal to the varactor diode, but it offers a very high impedance at high oscillator frequency. Therefore, the oscillator circuit is isolated from the DC bias and modulating signal. I believe that this is clear to all. Now the part is frequency stabilized FM generator using VCO, that is voltage controlled oscillator. So the figure shows the automatic frequency stabilized FM generator. The output of VCO is applied to the mixer along with that of a crystal oscillator. At the mixer output, we get the following four frequency components. Number 1, FCR. Number 2, FVCO. Number 3, FCR plus FVCO, and number 4 FCR minus FVCO. Then this mixer output is applied to a frequency discriminator and a low pass filter. So the question is, what is frequency discriminator? So this is a special type of device which produce an output voltage, the amplitude of which is directly proportional to the frequency of its input. The low pass filter that follows the frequency discriminator will eliminate the ripple contents in the output of the frequency discriminator. Why? To produce a ripple free control voltage at its output. So when FVCO is equal to FCR, then output of mixer FCR minus FVCO equals to 0. Hence the output voltage of frequency discriminator is 0, and hence the control voltage at the output of the low pass filter is also 0. Thus, this circuit will maintain the VCO frequency constant equal to the crystal oscillator frequency FCR. If the VCO frequency deviates above or below FCR, then the DC control voltage at the output of the LPF will be adjusted automatically to bring FVCO, that is frequency of VCO, close to crystal frequency. And there are some drawbacks of direct method for FM generation. It is not easy to get a high order stability in carrier frequency. This is due to the fact that generation of carrier signal is directly affected by the baseband or modulating signal. And also another one is the non-linearity of the varactor diode produces a frequency variation due to harmonics of the modulating or baseband signal, and therefore the FM signal is distorted. Despite all above drawbacks, the direct method is utilized. Why? For high power FM generation in several applications. Now the part generation and demodulation of pulse amplitude modulation. We know that in analog modulation systems, some parameters of a sinusoidal carrier is varied according to the instantaneous value of the modulating signal. In pulse modulation methods, the carrier is no longer a continuous signal but consists of a pulse train. There are two types of pulse modulation systems. Number 1, pulse amplitude modulation, and number 2, pulse time modulation. In pulse amplitude modulation, the amplitude of the pulses of the carrier pulse train is varied in accordance with the modulating signal, whereas in pulse time modulation, the timing of the pulses of the carrier pulse train is varied. There are two types of PTM as under: pulse width modulation and pulse position modulation. In pulse amplitude modulation, it may be defined as that type of modulation in which the amplitudes vary according to instantaneous value of the modulating or message input. In fact, the pulse in a PAM signal may be of flat type or flat top type or natural type or ideal type. And now the demodulation part of PAM. As discussed earlier, demodulation is the reverse process of modulation, in which the modulating signal is recovered back from a modulated signal. For pulse amplitude modulated signals, the demodulation is done using a holding circuit. Figure shows the block diagram of a PAM demodulator. In this method, the received PAM signal is allowed to pass through a holding circuit and a low pass filter, as shown in the figure. Here, the switch S is closed after the arrival of the pulse and it is opened at the end of the pulse. In this way, the capacitor C is charged to the pulse amplitude value and it holds this value during the interval between the two pulses. But there are also some drawbacks of a PAM signal, that the bandwidth required for the transmission of a PAM signal is very large and noise cannot be removed easily, and also since the amplitude of the PAM signal varies, therefore this also varies the peak power required by the transmitter with modulating signal. I believe that this is clear to all. And now pulse width modulation. The other type of a pulse analog modulation is the pulse width modulation, where the width of the modulated pulse varies in proportion with the amplitude of modulating signal. The block diagram here can be used for PWM. Here a sawtooth generates a sawtooth signal of frequency Fs. Therefore, the sawtooth signal in this case is a sampling signal. It is applied to the inverting terminal of a comparator. The comparator output will remain high as long as the instantaneous amplitude of xt is higher than that of the ramp signal. This gives rise to a PWM signal at the comparator output, as shown in the figure. Here it may be noted that the leading edges of the PWM waveform coincide with the falling edge of the ramp signal. And now the detection of PWM signal. The signal is applied to the pulse generator and which regenerates the PWM signal. Thus, some of the noise is removed and pulse squared up. The regenerated pulses are applied to a reference pulse generator or synchronous pulse generator. These pulses are synchronized to the PWM pulses but delayed by a fixed interval. The regenerated pulses are applied to the ramp generator. Then the pulses are also applied to the adder. The output of the adder is then clipped up to generate a PAM signal at the output of a clipper. A low pass filter is used to recover the original modulating signal back from the PAM signal. There are also some advantages and disadvantages. Advantages are very good noise immunity, synchronization is not essential, and it is possible to reconstruct the PWM signal from a noise. Disadvantages: due to variable pulse width, the pulses have variable power contents. And avoid any waveform distortion, the bandwidth required for the PWM communication is large to bandwidth of PAM. Now, the next part is generation and detection of pulse position modulation. The PPM signal can be generated from PWM signal as shown in the figure. The PWM pulse obtained at the comparator output are applied to a monostable multivibrator. Why? Because the monostable is negative edge triggered. Hence, corresponding to each trailing edge of PWM signal, the monostable output goes high. It remains high for a fixed time decided by its own RC components. Thus, as the trailing edge of the PWM signal keeps shifting in proportion with the modulating signal xt, the PPM pulses also keep shifting. And now the demodulation of PPM. The noise corrupted PPM waveform is received by the PPM demodulator circuit. The pulse generator develops a pulsed waveform at its output of fixed duration and applies this pulse to the reset pin R of a SR flip-flop. A fixed period reference pulse is generated from the incoming PPM waveform and the SR flip-flop is set by the reference pulse. Due to the set and reset signals applied to the flip-flop, we get a PWM signal at its output. The PWM signal can be demodulated using the PWM demodulator. Also, there are some advantages of PPM, that it has good noise immunity and it is possible to reconstruct PPM signal from the noise contaminated PPM signal. And next, due to constant amplitude of pulses, the transmitted power always remains constant. It doesn't change as it used to in PWM. So, disadvantages of PPM: large bandwidth is required to ensure transmission of undistorted pulse. I hope this is clear to all. And now the performance comparison of PAM, PWM and PPM. Amplitude of the pulse is proportional to amplitude of modulating signal in PAM, and in PWM width of the pulse is proportional to amplitude of modulating signal, and in PPM position of the pulse is proportional to the amplitude of modulating signal. And number 2, the bandwidth of transmission channel depends on width of the pulse. Next, bandwidth of transmission channel depends on rise time of the pulse in PWM, and in ppm the relative position of the pulse is proportional to the amplitude of modulating signal. And next point, noise interference is high in PAM, we see earlier, and in PWM noise interference is minimum, and in ppm noise interference is also minimum. And next, PAM, it is very easy, that similar to amplitude modulation, PWM similar to frequency modulation, and ppm similar to phase modulation. I believe that this is all clear to you, and if you have any doubt, please feel free to reach me anytime. Thank you. Thank you.